Hi, let's talk about quantum revolution and let's talk about what the industry is doing currently. Let's start off by doing an informal science and coffee video. And if you're Linux fans, that's the mascot. So we can go back 100 years and talk about many different things related to quantum mechanics. And we can talk about the infancy of the field. In my chemistry courses, I learned a lot about the photonic effect by Einstein. I learned about Boltzmann's constant or law. I learned about many other statistical, chemical, physical phenomenons that are very important for quantum, but not so much the focus of this channel or this video, because over the last 5 years we transitioned from just using quantum mechanical phenomenon and understanding what quantum mechanical phenomenon is to now we're actually applying it in large systems. And as of yesterday, SUEX alluded to a possible prototype. So we need to transition just from what quantum mechanics are to how they're being used in large systems. Over the course of the next few months, we're in a transition from qubits to 100 years ago to what quantum mechanics are, to how they're being used in circuits, to algorithms that are using circuits efficiently, to what quantum computers and quantum networks are. So let's really focus on the last 5 years. Over the last couple of years, I've been focusing closely on this. I've been invested, and I found it interesting. When I was deployed, I created a few RFCs, which are requests for comments. If you're familiar with the IT field, that's creating a draft to try to come up with a new standard or technology. And this helped me allow the focus on quantum mechanics and the field of quantum computing. So when I was deployed in Africa for the US Air Force, I spent a lot of time trying to study up on this to get better prepared to help the Air Force when I came back. Unfortunately, that was not a direction I was able to pursue at the time. There were other mission critical needs. So now that I'm out, I can start pursuing some of my dreams. During my studies, I came across an intense race between IBM and Google from about 2015 or 16 to about 2018. During this time, IBM and Google were back and forth. It was hard to tell who was going to come out on top. Seemed IBM fell short and Google took the lead with Bristlecone. And that was 72 qubits, and it was phenomenal. It was a phenomenon at the time. It's crazy. After that, it seemed Fort Meade allowed IonQ out of Meade in Maryland to enter the race with 128 qubits. This was beyond anybody's wildest dreams at the time because we were looking at 72 qubits, and as you'll see later when we talk about qubits and quantum mechanics, it works on an exponential scale. So IonQ coming in at 128 qubits was fascinating. It couldn't be compared, and it was unparalleled at the time. Then the government cleared Honeywell to enter the field. I believe it was last year. And once again, they came in with twice the quantum volume. And so for quantum computing, we're not talking about Moore's law in the sense of, okay, how small the circuit is or how small the chipset is. But now we're talking about something that uses multiple statistics to then interpret quantum Moore's law, which actually has been found to follow similar similar trends, and it's one of the research avenues that IBM's looking at to try to determine if Moore's law, if quantum follows Moore's law, and they're finding that it does, but not in the sense that we traditionally think. So not only did Honeywell enter, but over the last few years, you have Canada's Xander group that really focused on quantum AI or artificial intelligence. Took it by storm at the time. And they have something called PennyLane that is the interface that associates with some of the AI research, quantum AI research that they've been doing. We'll talk about the different aspects associated with programming languages for the quantum field. Then you have Australia's SILEX systems that really made a shocking revelation. They realized that you don't actually have to change the physical layer as much as you think. So most people will associate quantum with transitioning away from silicon. And Australia is saying, hey, we have all this silicon. We like to create qubits within silicon. And they're doing a pretty good job over there. So it's far behind some of the other research, but it's a different area that allows quantum for IoT devices or for smaller devices, and it's pretty promising. So then in 2017 or so, you saw UK's SUEX University come out with a completely quantum blueprint, quantum information system blueprint. It was fascinating. It was very detailed, and it's laying the foundation that we're seeing today. So as of yesterday, they have shown that they may actually be on the way or have broken through with a quantum computing prototype. Yesterday they released an article saying scalable helium research project that paves the way for the quantum information systems moving forward. And this would be pretty fascinating, as Turing was able to help develop, I think help Manchester in UK develop the first computer. I'd have to do some research on that and come up with what that actually means. But they actually got it from cryptanalysis at Bletchley Park, breaking Lorentz machine, not the Enigma. Lorentz was more complicated, and it was actually the first unofficial computer for the world, and some exciting research. So moving forward, in our lectures, we'll be talking about a couple different companies and a national lab. So we're going to bounce back and forth between Google, IBM, Xandar, SUEX, and Oak Ridge National Laboratory. So why did we pick these? It's pretty simple. There's a lot of resources out there. Seems like everybody is doing quantum research, and it's hard to keep up with what the latest fad is or who has the best architecture. Essentially, Google's been the leader in hardware for a while, so we're going to focus on their programming language, which we'll talk about later. Also, IBM probably has the best documentation out there, so we're going to start with IBM's research and go from there. They have tons of great resources for getting started in quantum computing. Google specifically lays out that you got to have a background knowledge in quantum architectures and information systems in order to even get started. So we'll build up to that, but it's definitely not the one you start with. It's a stepping stone. Going further, Xandar, and if I'm saying that incorrectly, please correct me in the comments. Over the years, I've always had difficulty with that, so doing the best I can, but I'm here to help you guys with knowing and applying the research that I find interesting. So Xandar and Oak Ridge has invested a lot of time in quantum AI. Oak Ridge is probably the standard for quantum AI. They've listed out and laid out a really good game plan for quantum AI, and I'd recommend going there if you have any questions beyond what is AI. And currently, NASA and Oak Ridge are developing and have been developing since I was in Africa, neuromorphic quantum computing. And that's something we'll touch on at the very end. Basically, the pun was intended that they're changing the way we think because it's supposed to be representative of quantum mechanics and the brain. So depending on what you think, some people think some people think our brain acts like a quantum computer and that we can represent a fully quantum architecture by how our brain interacts with itself. Some promising research. We'll spend some time on it and see how it goes. Lastly, I'd like to talk about that SUEX is still the leader in quantum information systems and quantum networks. I would have said MIT, but a lot of the research is watered down when it comes to network designs and implementations of networks. Currently, their last paper was pretty unintelligent. I wouldn't recommend going to MIT as a source, but I would recommend going to Xapka software, and that's something you should look out for. It's actually started out at MIT, like an ex-Air Force guy like me, and it's really cool that we're getting to see some new startup companies looking at software design, because that's really where the future is. It's not based on the hardware, it's based on the software. So we have dozens of companies that have created reliable software, and it's really about what we can do with it now. And that's what this course is about. It's trying to teach you what we can do with it. Also, some really cool research has come out of Australia for quantum TCP. Unfortunately, you're not supposed to represent quantum networks with classical systems, because you're supposed to be capitalizing on quantum mechanical properties, and it just seems like they took TCP and just applied it with quantum system, quantum network, and that's really not what you're supposed to be doing. And based on quantum entanglement itself, TCP should be intrinsic of layer 1, and essentially there shouldn't be as much overhead for layer 4. So the segments, or TCP segments, should already be implemented within a quantum entanglement between one connection to another. And that's something we'll explore later on. And please follow along on the channel. I look forward to seeing what you guys say. And like I said, correct me whenever you hear something that's not what it's supposed to be. I'm more than happy to make corrections and redo this video, but I believe I can help you guys get to where you want to go and to learn a lot along the way. I look forward to working with you.